Assalamu alaikum everyone. I hope you're all doing well. So, if it were not for the curiosity of our minds and endless desire to seek the answers, we would not have stumbled upon the method of making sense of the universe around us. We call that method science. We have found that we are a part of a universe that is in fact understandable if only we are willing to observe a little closely. NUST Physics and Astronomy Society, for that very purpose, brings to you numerous opportunities to enhance your understanding of how the universe works and tries to bring you answers to the big questions. Keeping up with our tradition of encouraging scientists, we have arranged yet again a session of talks by NUST's very own final year physics students, giving them a chance to share their final year projects with us. I, Namra Salim, will be the host to the second session of the series, and as our guest speaker, we have Alizah Gul Memon. Alizah is currently a part of NPAS, and she is a science communicator, as well as a part of Popular Science, Spectroscience Magazine, and Earthly Perspective Magazine. She hopes to become an astrophysicist and wants to use quantum computing in her research. Today, she will be enlightening us regarding quantum circuits and quantum safe encryption. Following the session, we will have a Q&A session and we hope to get you answers to all your queries regarding the topic. You can post your questions throughout the session. So over to you, Alize. You may start.
Thank you, Namra. I was a bit flattered by the introduction. Assalamu alaikum, everyone. I hope you all are doing well. Aap sabko Juma Mubarak. It's the last Friday of Ramadan. So let's move on to the presentation. My topic for today is quantum circuits of quantum safe encryption. And I realize that it has a buzzword, quantum, in it that people usually find very fascinating. If nothing else, like astronomy and quantum are two things that get people very excited about physics. So the contents of my presentation are as follows. We'll be seeing them in detail, so I'll go over them as we go along. Now, what do we mean by the word quantum? Now here we're saying that we're using the properties of quantum mechanics in all that we're doing, and the major properties that are involved are superposition, entanglement, and interference. Now, quantum computing is a way of computing using the laws of quantum mechanics. And why are we so interested in quantum computing? Because, well, the universe uses principles of quantum mechanics, so we would want to have, a system that kind of replicates the things that we see around us. Now, talking a bit more about the quantum properties that we saw, superposition is the ability of a quantum system to be in multiple states at a time until measured. And the famous experiment that we have for this is it's a concept basically of Schrodinger's cat. And here's a little comic I've attached as well. So talking a bit about the experiment, it involves a cat being locked up in a box with a radioactive element, and that element is attached to a trigger that, when the element decays, a knife hits the cat and the cat dies. But until you open the box, you don't know if the cat is dead or alive. So that's kind of how superposition works. And yeah, here's the comic if you want to read it. बाकी फिर entanglement क्या होती है? When a group of particles interact in a way such that the quantum state of each particle of the group cannot be described independently of the state of the others. So you can tell by one measurement what the other is, what the other particle is going to be, like what state it's going to collapse in. And here's an illustration of entanglement. It's kind of as if those particles are connected with one another. And here's a funny post I found a few months ago. So it also explains entanglement in one way at least. फिर interference पे आ जाते हैं, a phenomenon in which two waves superpose to form a resultant wave of greater, lower or the same amplitude. So we have constructive interference, destructive interference as shown in the images, and in some cases we have waves of the same amplitude. Now, quantum supremacy. So scientists around the world now, quantum computing has a lot to offer, and it's something that people are starting to explore quite a lot. So what's happening is that people are trying to find ways in which quantum computers can outperform classical computers. So there was a time when Google came forth and said that it has solved a problem in a matter of a few seconds, I think, or minutes, that would have taken classical supercomputers over 40,000 years in theory to calculate. And then there were other competitors. We know about IBM. Then Honeywell came forth and said that we have another quantum computer. It's a bit different to what you guys have been doing, but it's also like very efficient, maybe even better than what you guys have been up to. And then China also came in and it said it achieved quantum supremacy with the world's fastest quantum computer. So like these are some of news articles. Like if you want to read more about what quantum supremacy is, so you should definitely check it out. It's very interesting. Now, coming to the post-quantum era, what is it about? And like, um, yeah, let's get into it. So, post-quantum cryptography. Now that we know that quantum computers have come into the picture, some things are not as safe as they used to be. Now, the popular algorithms of the time and currently, they used to involve integer factorization problems, discrete logarithm problems, and elliptic curve discrete logarithm problems. But when people started working on quantum computers and when algorithms like Shor's algorithm came out, what happened was that a lot of the principles on which some of the encryption was done, that came under threat. So, for example, integer factorization, you'd have like a very complex number and then you'd find the factors of it. But then Shor's algorithm could do it in much lesser time, and that kind of posed as a threat to the encryption that was being done using such problems. And yeah, like right now, the quantum computers, they lack processing power to break any real cryptographic algorithm, but based on the pace at which this field is evolving, it's going to be a matter of time before we're going to have quantum computers that are going to be, a threat for the classical algorithms that we have. So that's why people are starting to work on algorithms that are going to be safe in a post-quantum environment. And yeah, so most symmetric cryptographic algorithms and hash functions are relatively safe against quantum computers. And Grover's algorithm is basically something like you find the particular function that you're looking for. It's a way of doing that easily. So while the quantum Grover's algorithm does speed up attacks against asymmetric ciphers, when you double the key size, that can efficiently block these attacks entirely. So post-quantum cryptography does not really need to be too different from what current symmetric cryptography is. Now, let's talk a bit about this encryption standard that we've been studying in a bit of detail. We'll see what the AES is, different variations of it, major components, and how each of these work. So the Advanced Encryption Standard, like we said, that symmetric key cryptography, it's relatively safe. So this is one of those encryption standards that is still very safe. And it's one that WhatsApp is using for its end-to-end encryption, as you might have seen on your phones. It's something the US government has been using to keep its documents and other information well confidential, and it's a block cipher. So what that means is that instead of encrypting and decrypting information bit by bit, um, stream ciphers, what a block cipher does is it interacts with information in the form of blocks. So we have 128-bit blocks with a key of predetermined length. So the key can be of 128 bits, 192 bits, or 256 bits. And the key size used for an AES cipher specifies the number of transformation rounds that convert the plain text to the ciphertext. तो आपके पास जब 128 बिट्स की होती है तो आपको 10 राउंड्स चाहिए होते हैं, 192 के लिए आप 12 राउंड्स यूज करते हैं, and then when you have 256 bits in your key, so you have 14 rounds to encrypt that information and make it unintelligible for a third party that's trying to intercept it. And the 128-bit blocks are 4 by 4 state arrays. You can see the matrix on the side. Let me explain it a bit. So yeah, bit. So 1 byte is equal to 8 bits. So when we have 128 bits in the block that we're considering, we have 16 bytes in total, which translate to 4 words. So again, 8 bits equals to 1 byte, 4 bytes equals to 1 word, and then this is how we're dealing with the information that we need to encrypt. Actually, now we have a video. I hope it plays here, otherwise I'll just share it in my browser. Just a moment. Right. Is my screen visible? Again.
Yes, it's visible.
Okay. So I'll just play the video as soon as I see it in full screen. I'm really sorry, my computer is a bit stuck, so acha say it's about to play, hopefully. So while the video, it's playing. So this is a video that kind of helped me understand the AES much better than I did in the past few months. And I thought it would be helpful to see it before I go on into the detailed explanation of what the protocol is about. Yeah, I'm still having trouble loading it. I just say yeah. So what the encryption protocol does is it takes plain text and turns it into ciphertext. Now, this is the 128-bit block that needs to be encrypted, and this is the cipher key that we use, which has the different number of bits that we talked about just now. And we use hexadecimal notation as opposed to binary. Right, so in the encryption, what we are doing is we have the initial state, and then we're using different operations using our cipher key to, jumble the information up so that it's secure in one way. And what happens is that it's not just like we perform these operations once. They happen again and again for the number of rounds based on the bits in our key, and until we have our ciphertext in the end. So this is what the animation is also showing. Right. So these are the 4 major transformations. SubBytes, which is short for substitution of bytes. Now we have an S box, which is basically where we're substituting our bytes from. Now it's an entire table in hexadecimal values, hexadecimal meaning that just like we have binary, which have 0 and 1 to represent different numbers, we have this hexadecimal notation which goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So we have combination of these to represent different values. Now what we're doing is substituting each byte from the table based on where it is. And then we have shift rows. And as the name suggests, we're just shifting different bytes in the rows. And then there's mixed columns. Again, we're multiplying each column by a matrix, and what this multiplication is happening in is called the Galois field. So it's not like ordinary multiplication, because we have 8 bits in 1 byte. That's why we're using this particular field for the multiplication. And this is one of the operations that basically makes the AES uncrackable because of its complexity. So after we multiplied all the columns, we see the add round key. So what we're doing is that our state block, we're XORing it with the round key that we have. XOR is basically like doing binary addition, and then and this is the result that we get. So we do it for each of the columns that we have. So see, this is what makes the AES interesting and also very complex, is that we're not just doing all these operations once, we're doing them 10, 14, or 12 times. So like after each round, we're getting different final results until we finally reach the ciphertext. So we talked about how we have a different number of bits in the keys that we might be using. And one thing I think I didn't mention before was that we use more bits or like a larger key when we have more crucial information that needs to be protected. So right now, like we saw that the state block is of 128 bits. So we're going to interact with our keys in the same sized chunks, and we're going to be expanding the key that we have so that it can be used in different rounds. So what's happening is that we're having these different operations so that we can use a different key in each round. What we did first was that in our first block, like the last column, we singled it out, we rotated the words in it, and then we substituted them from the S box. And then we XOR it, and then we XOR it with the first column, and then we XOR it again with Archon. This is another reference table we have, so to speak. And so the animation is kind of self-explanatory. I'm just going to comment a bit and then I'll let you enjoy the rest of it. So like for the next column, we just take that and like the column, 2 columns away, and then we're just continuing the process. So this goes on and on until we reach the round key that we require. And that is all for the little video. I'm just going to go ahead and share my slides again. Okay. Can you see the PowerPoint presentation like slideshow mode में नजर आ रही है आप लोगों को या फिर are my slides visible वैसे?
Yes, it's, no, actually, we can still see the video.
Let me just move my slide. अभी आपको नजर आ रहा है advanced encryption standard
Yes,
लिखा होना
it's
चाहिए?
fine now.
Oh, perfect. Thank you. Right. So as you saw, like all the jumbling up we did, it kind of reminded me of a Rubik's cube. It's something that as a kid, at least, okay, so it's something that at least I couldn't solve. And actually, I'll just need a minute. My video is still playing. अच्छा सही है, I'm back. So like this is kind of like a Rubik's cube के आप एक simple Rubik's cube for example किसी बच्चे को देते हैं और वो बहुत बुरी तरह से उसको mix करता है, then they give it to you again and then you're just left confused के how do I turn it back to normal. अभी खैर we have videos on YouTube for Rubik's cubes लेकिन फिर as you saw AES is far more complex than that, so that's why it's very secure. So we saw this in detail in the video. This is just like the definition of everything. तो हमारे जो operations थे सारे bit blocks पे वो add round key, SubBytes, shift rows और mixed columns थे. और add round key का ये था कि each byte of the state is combined with a byte of the round key using bitwise XOR. SubBytes substitution of the bytes. So each byte is substituted with another according to a lookup table. फिर shift rows था कि आपकी जो last 3 rows हैं of the block they're shifted. एक रो को आप एक बाइट को इस पे शिफ्ट करते हैं, एक में 2 को और फिर एक में 3 को as we saw. And then mixed columns, a linear mixing operation on the columns of the state using a predefined matrix. And like again as we saw कि ये फिर एक सीक्वेंस है कि आपके पास पहले प्लेन टेक्स्ट आता है, फिर आपकी की एक्सपेंशन होती है कि आप जो आपकी इंफॉर्मेशन है आप उसको इस तरह से की को आप एक्सपैंड करें ताकि वो हर राउंड के लिए आपके पास एक डिफरेंट की आ रही हो. एंड देन आप इनिशियल राउंड में आप ऐड राउंड की वाला ऑपरेशन यूज़ करते हैं, फंक्शन यूज़ करते हैं. फिर आप 9 राउंड्स के लिए या 11 राउंड्स के लिए या फिर 13 राउंड्स के लिए डिपेंडिंग ऑन योर की साइज you use SubBytes, shift rows, mixed columns and add round key. And then in your final round you use SubBytes, shift rows and add round key. अब इसमें one thing you might have noticed is that add round key पहले वाले राउंड में यूज़ हो रहा है और आखिरी वाले राउंड में जो mixed columns यूज़ नहीं हो रहा. तो this is just to make our encryption symmetric. So yeah, that's basically the reason why the functions have been used this way. And then you unload your state array in the form of your ciphertext that can now be sent to another person. तो की एक्सपेंशन अगेन ये भी हम लोगों ने देख लिया था. तो ये उसका एक algorithm of sorts if you want to check it out. This is kind of like the pseudo code for it or like the actual code. Okay. And ye ki based on the paper that we are studying, these are keys required to construct each key in the AES. So K4 को construct करने के लिए हमें K3 और K0 की ज़रूरत है. Like we saw in the video how we were using different columns to construct new ones. So this is something that they've done for the quantum circuit of this encryption standard. And again, this is the G function जिसको हम use कर रहे थे when we were XORing the columns to make the next key. And this is like the visual representation of the functions. तो यहाँ से फिर आपकी की के साथ ये XOR होके ये फिर ये नया ब्लॉक बनाता है और फिर substitution bytes के ये S byte से वो replace होके फिर you get the new block. Shift rows again कि आप लोग एक बार shift करें, दो बार या फिर तीन bytes को shift करें, so that's how you get the next block. And then mixed columns. So this is the specific matrix that we're multiplying with. And again, the multiplication is not simple. It's done in the Galois field where we have to limit the size of each byte. Like after the multiplication, if the value is larger, then we divide it by an irreducible polynomial to get our required result. Now let's move on to quantum gates. Those of you from a physics background might already know this, but I'll just go over this in a bit of detail. अब जिस तरह हमारे क्लासिकल कंप्यूटर्स में नॉट गेट होता है दैट फ्लिप्स द 0 to 1 या फिर 1 to 0, तो क्वांटम कंप्यूटर्स में भी वी हैव द एक्स गेट दैट डज द सेम टू क्यूबिट्स. अब क्यूबिट्स जो होते हैं क्वांटम कंप्यूटर में बिट्स होते हैं, तो वी हैव लाइक द 0 स्टेट एंड द 1 स्टेट एज अपोज टू आवर सिंपल बिट्स. और जो 0 स्टेट है वो अगर कॉलम वेक्टर के तौर पे आप दिखाएं तो इट्स 1 0, और 1 स्टेट जो है वो 0 1 के तौर पे होती है. And we show our qubits in this globe thingy that we call a block sphere. उसमें ये कि जब आपका qubit जो है वो 0 वाली साइड पे है तो वो flip होके नीचे 1 वाली साइड पे आ जाता है. That's kind of how the X gate works. फिर we have the Hadamard gate. तो this is where superposition happens कि आपके पास अगर एक simple 0 qubit हो तो उसको आप एक superposed state में कर देते हैं. तो या फिर if you have your one qubit, so that also gets superposed. So superposition, I might not be describing this correctly, but like in some ways it's kind of like okay, instead of dealing with the information like individually, you now have like a combination of both your qubits. I hope I explained it correctly, but yeah, that's kind of how it is. You can look it up in detail if you're interested. बाकी फिर Z gate जो है, it's a rotation around the z-axis on the Bloch sphere by pi radians, and it's sometimes called the phase shift gate. So this is how it's represented on the Bloch sphere. And then we have the control NOT gate. Now we know what the NOT gate does. It flips the bit based on the value it initially has. The control NOT gate, what it does is that it needs a control first. So like if your first bit is 0 and the second bit is also 0, it won't do anything. But if your first bit is 1 and your second bit is 0, so it's going to flip the 0 to a 1. And we for qubits we can represent this as tensor multiplication as done in the bottom of the slide. So that's the resulting state that we get. And there's the control Z gate. We have the control, and then we have the phase shift operation, and then there's the control NOT gate. So in this gate we have two controls, and then the third bit is the one that is going to be flipped. And this control NOT gate is also called the Toffoli gate, and it's one of the integral gates that we're studying when we move on to cost reduction. So this is a name you might want to remember. We'll be going through it again in the next couple of slides. और ये कि इसके जो नीचे अगर आप लोग देखें एक सर्किट डायग्राम है, उसमें ये कि आपके जो पहले दो बिट्स हैं देर एक्टिंग एज अ कंट्रोल बिट्स, एंड देन आपका जो आखिरी बिट है उस पर आपका एक्शन हो रहा है. तो मतलब जिस तरह होता है कि अगर आपके पहले दो स्विचेस अगर ऑन है तो तीसरा ऑन होगा, पहले दो में से कोई एक भी ऑफ हो गया तो फिर तीसरा जो है ऑन नहीं होगा. I hope that's kind of an easier way to understand what's going on here. फिर quantum equivalent circuits of classical logic gates. NOT gate की हमने बात कर ली थी कि X gate is the quantum equivalent of the NOT gate. AND gate के लिए ये कि control NOT gate use हो रहा है. इसका truth table भी इसी तरह से ही बनता है कि like unless आपके दोनों जो है inputs they're not the required inputs, you don't get the required output. So like until and unless आपके दोनों inputs जो हैं they're not 1, you don't get a 1. There's a NAND gate as well. So it's kind of like the opposite of the AND gate. तो इसीलिए आपका सारा जो है आप एक Toffoli gate यूज करें और उसके फौरन बाद आपने एक NOT gate लगा दिया है, तो मतलब आपका जो भी रिजल्ट आया था उसको फ्लिप कर देता है, तो वो एक NAND gate बन जाता है. Then there's the OR gate, control NOT gate. You add two control NOT gates and one Toffoli gate, and this is what you get. Then there's the XOR gate. This is something I mentioned before कि हम XOR करते हैं, तो this is how we show it on a quantum circuit. XOR basically exclusive OR gate के exclusively, और मतलब आपके सिर्फ एक जो है आपका for example switch वो on होना चाहिए, अगर दोनों on हुए तो फिर you're not going to get the required output. Then there's a NOR gate. So this is how we show it. So that there's one control NOT gate on the second bit bit, there's one control not gate on the first bit, and then there's a Toffoli gate followed by a NOT gate. So this is the truth table that we get for the NOR gate. And I'm sorry, I mentioned this before. Q is equal to quantum register. ये सारी जो चीजें, this is how we make this circuit on a quantum computer. So these are like, this is kind of like the code for it. फिर आ जाते हैं cost of the circuit पे. The quantum cost of any reversible circuit can be measured by the number of elementary gates used to build this control power n NOT gate, which are considered as the number of the used 2-qubit gates. अब ये होता है कि qubits जो होते हैं, they're two energy level systems, और ये कि we're working at them at a certain temperature, and there's a certain amount of time up to which we can work with those qubits. और ये कि जितने ज़्यादा qubits involved होते हैं उसकी एक अलग cost होती है, तो मतलब that kind of makes the circuit harder to work with. तो ये कि मतलब even if AES जैसे quantum circuits जो हैं, they can be crackable theory में, लेकिन ये कि practically it's not that feasible कि आप इतने सारे qubits use करें for that purpose. That's also why Grover's algorithm का जो mention हुआ था शुरू में, उसमें भी ये था कि आप जब bits increase कर देते हैं तो फिर वो Grover's algorithm भी it's not as effective to crack the code. तो अब इसमें हम इसीलिए cost को देख रहे होते हैं. तो we adopt two methods for calculating the quantum cost. एक तो cost 015 metric है और cost 115 metric है. और इसमें remember when I said Toffoli was important, तो ये कि हम एक NCT based reversible circuit देख रहे हैं कि इसमें हमारे जो सारे major parts हैं हमारे AES वाले circuit के, they can be represented through a series of NOT gates. The N is for NOT gates, C is for control NOT gates, and T is for Toffoli gates. तो ये तीन हम लोग gates use करके अपना पूरा AES के circuit को दिखा सकते हैं. And cost metric का ये कि आपका जो NOT gate है उसकी cost आप 0 consider कर रहे हैं, control NOT gate की 1 consider कर रहे हैं, Toffoli की आप 5 consider कर रहे हैं, based on the number of controls that you might have. और फिर cost 115 metric का ये कि आपका NOT gate भी 1 consider हो रहा है, control NOT भी 1 और Toffoli 5 consider हो रहा है. अच्छा, comparison के लिए, अच्छा, I'm kind of fond of games, so you might see why I mentioned them in my slides. तो ये कि Jenga को देख लें कि when you have a tower of Jenga, एक तो ये basic आपके पास on your left जो tower है, that's how you would usually make it कि आपके सारे इसमें blocks use हो रहे हैं. But then as the game progresses, आप जो होते हैं blocks निकालते जाते हैं. And in this case, imagine कि आप जो blocks हैं वो निकाल के ऊपर नहीं डाल रहे हैं, आप बस blocks निकाल रहे हैं और देख रहे हैं कि what are the minimum number of blocks जिस पे ये tower फिर भी खड़ा रह सकता है. तो that's kind of how cost reduction works. इसमें ये कि there are some qubits that are not going to be required after a certain number of cycles. तो उसका ये कि when they're not needed, you can just use them somewhere else. So that's kind of how we're making our circuit more cost efficient. और फिर that's kind of what they've done in the reference paper that we're studying as well. कि इससे पहले भी AES के जो different quantum circuits के models बने थे उसमें एक certain number of qubits involved थे, लेकिन फिर जो बाद में लोगों ने research की उन्होंने देखा कि कुछ चीज़ें उसमें से ऐसी हैं जो redundant हैं या फिर ऐसी हैं जिनको हम निकाल सकते हैं तो circuit फिर भी वैसे ही काम करेगा. तो that's why they've come up with a condensed form, you might want to call it. So that's how we get to this Jenga tower on the right. And then there's the comparison. अब जो table 2 है, these are the two reference papers before the one that we were studying. इसमें ये कि they've used जिस तरह AES 128 आप देख लें कि इसमें 128 bits आपकी यूज हो रही है की में, तो इसमें NOT gate number of NOT gates जो हैं 1456 हैं, control NOT के जो हैं 1,66,548, Toffoli ये सारा. तो ये कि फिर ग्रासल वाला जो पेपर है इसमें ये सारे इनके यूज़ हो रहे हैं qubits वगैरह. And then Al-Mazrui, what he and his team did, they reduced the number of gates and qubits that were involved. तो as you can see जिस तरह नॉट गेट को अगर हम देख लें कि 1456 से आप जो है 1370 पे आ जाता है, एंड देन कंट्रोल नॉट जो है यहाँ पे डिक्रीज होने की जगह इंक्रीज हुआ है, बट देन टोफॉली गेट्स भी डिक्रीज हुए हैं, and then Toffoli gate, this is Toffoli depth is also something that we see in quantum circuits. So this is something I haven't touched on in my presentation, but I can explain it if you like in the Q&A session. अच्छा, और फिर इसके बाद टेबल 1 पे अगर आ जाएं, तो टेबल 1 is the model that we're studying. What they've done is further reduce the cost, और फिर इसमें ये सारी चीज़ें उन्होंने बताई हुई कि कितने qubits इन्होंने यूज़ किए हुए. तो इफ़ यू जस्ट कंपेयर दिस विद ग्रासल, तो ये कि जिस तरह ग्रासल में AES 128 की जो क्यूबिट्स अगर आप देख लें तो देर 984, लेकिन फिर AES 128 जो ये वाला पेपर हम लोग देख रहे हैं इट्स 864. तो यू कैन सी दैट देयर इज अ रिडक्शन, एंड देन 1112 से आप 896 पे आ रहे हैं, तो लाइक देयर इज अ ह्यूज डिफरेंस हियर, एंड देन 1336 आप 1232 पे आ रहे हैं. तो you know that's kind of how things are progressing, or maybe there will come a time where someone else comes up with a more cost efficient circuit where they reduce the number of gates and qubits even more. So that's kind of one way of seeing like how quantum computing can progress, like what the potential is. And then maybe while aap jab itna cost reduced circuit banate हैं, and you kind of figure out how to do the work with less resources involved, so maybe there can come a time when we finally manage to crack the uncrackable AES. So that's for you guys to figure out. Maybe if you're interested, this is something you can consider working on in the future. And I guess that's all for my presentation. If you guys have any questions, feel free to ask. Right. So I'll just stop. Wait.
All right, guys. So if anyone has any questions, you may ask them now in the chat box.
Let me see if I have something else to add in my own presentation until we get more questions. वैसे तो ये कि like if you have questions related to quantum, I thought like having quantum twice in my topic could have resulted in some questions because it's usually something exciting. But so if you want to see the comic, you can also check this out. And I think we have a question. Acha. So in the beginning, you mentioned number of transformation rounds. Could you please elaborate on that? And there's another question. Can you define a quantum computer? Let me just go to those slides. Quantum computer जो है, it uses the principles of quantum mechanics. जिस तरह हमारे पास जो bits होते हैं classical computers में, हमारे bits होते हैं classical computers में, they're just zeros and ones. But when we have qubits involved, इसमें आपने जिस तरह हमने different gate operations भी देखे थे कि we are using different properties of quantum mechanics in them as well. जिस तरह हम Hadamard gate देख रहे थे तो उसमें हम superposition वाली property use कर रहे हैं. And then there are other ways in which we entangle qubits as well, and then there's also interference involved. तो quantum computers क्या करते हैं कि वो quantum mechanics को use करते हैं, and then that's how they simulate real life problems. तो क्वांटम कंप्यूटर्स कई के एप्लीकेशंस भी इसकी बहुत ज़्यादा हैं एंड यू कैन यूज देम टू कंस्ट्रक्ट मॉडल्स इन लाइक केमिस्ट्री एंड बायोलॉजी एंड people have used them in astrophysics as well, something I'm also interested in. So yeah, that's kind of like the gist of how quantum computers work. क्वांटम कंप्यूटर्स के बारे में ये भी कि अभी फ़िलहाल IBM का अगर आपको बताओ, उन्होंने इंटरनेट पे they've offered people to use their quantum computer. So what you can do is actually write your code and then you can either simulate it या फिर आप असल क्वांटम कंप्यूटर से भी इसको कैलकुलेट करवा के you can get different results to your calculations. And then actually let me just check the next second question again. The number of transformations. अब ट्रांसफॉर्मेशंस हमने यहाँ पे गालिबन देखी थी जो हम की एक्सपेंशन की बात कर रहे थे कि AES के डिफरेंट वर्जन्स कह लें, AES 128, 192 और 256. इसमें क्या हो रहा है कि हमारी बस जो कीज़ हैं उसमें ज़्यादा बिट्स यूज़ हो रहे हैं एंड वी डूइंग दैट सो दैट आवर इंफॉर्मेशन कैन बी मोर सिक्योर. क्योंकि आप देख लें अगर आपके नंबर ऑफ बिट्स इंक्रीज हो रहे हैं कीज़ में तो आप उतनी ज़्यादा राउंड्स कर रहे हैं एंड वी सॉ दैट हर राउंड में कितने ज़्यादा ऑपरेशंस कितनी बार हो रहे हैं. तो that's kind of how the information is made secure.